Hi, my name is Tom Lever. Welcome to Little YOLO version 4, part 5 of how darknet and YOLO version 4 convolutional neural networks work. In this video, we're back to our little YOLO version 4 for viewers solution, and let's go into the details of how the method getLabelsCustom in the text test detector functionality works. In the last video, we changed the configuration, i.e. the input parameters, of getLabelsCustom to work directly with the names file, given that in little YOLO version 4, we don't need the coco.data file. So going to this method and taking a look, this method takes the coco.names path and outputs a pointer to an array of pointers to strings, to character arrays. And this array is a path list, or in our case, a names list that was converted into an array of this form. So this method takes in a path to a names file and generates a linked list with nodes where each node has a next node, a previous node, and a pointer to a string. And then that linked list is converted into basically a string array. The memory for the linked list is freed or deallocated, and the array is returned. So let me start here in our little YOLO version 4 for viewers by writing out the call. So we're declaring first a pointer to an array of pointers to character arrays called names, and defining names as the output of getLabelsCustom, and it takes path to names file. So now let's set up getLabelsCustom. Let's start with the header file. Our inclusion guard. Okay, and then let's take a look at this method signature. These are primitive data types, so we don't need any other inclusions right now, but we do need to define the method. So we're done with the header file. Setting up the source file. It's empty right now. Let's just make sure everything's working by including standard input output and saying that we want to print to console that we're using getLabelsCustom. Okay, and then here in test detector still doesn't know what getLabelsCustom is, so let's include its header file. And let's give this a shot. Build errors. Must return a value. Of course. Well, for now, let's return null pointer. Or this could also be return 0 because null pointer is a 64-bit or 8-byte address. And all the bits in that address are 0. Give that a shot. Okay, at least it's calling so far to getLabelsCustom. I'm going to take everything out for now that we don't actually need. We'll come back to this. I'm going to move this over here. This is the beginning of going pretty deep in submethods, so I want to stay organized up here. Okay, so the first part of getLabelsCustom is to take the file name to the names file and generate a linked list. Just because it's not immediately in my head, I'm going to include standard input output and then print the string file name, and we'll break the program there. I want to see, okay, yeah, this is the absolute path that is in the debug command line argument options for this solution. Taking that back out. All right, let us work on passing the relative path to the method getPaths, or in this case getNames, and generating a linked list called pathList. So first, let's declare list pathList. And this is actually a pointer to a list object. So here, we don't have list defined yet, so let's do that. And I'm going to keep things organized up here as well. Going to the definition of list. Okay, list is a class, basically. But in C and C++, we don't have classes. We have structures with type names and aliases. This could also be an object of type struct list with a sublist alias. So like list of network layers or something. It's still an object of struct list type, but it's now known also as a list of networks layers object as well. But I generally like this template. And for not using aliases. So let us define the list object template. And we can do this in a header file called list.h. Start off with our inclusion guard. And then we're defining the object type struct list with alias list, and the struct list objects have a size property, an integer, a pointer to a node object called front, and a pointer to a node object called back. Now we need to define node objects. I'm making sure all of my files are more or less in order as we go deeper. So I'm setting up now a object definition for a node object in a node.header file, inclusion guard. This node object contains a pointer to a string in our case, so a pointer to a name basically, and also has a pointer to a next node and a pointer to a previous node. So the linked list consists of nodes that are linked to each other. The first node is at the left of the linked list and has, I believe, null pointer as previous and the next node to the right as next. And then the second node in the list has the first node as previous and the third node as next, and then stepping back, the back node has null pointer as next node and the second to last node, second to most rear node as previous. And each of these nodes has a pointer to a memory location for a string. So we have the node object defined, we have the list object defined. You might think that this definition of a node object is somewhat recursive looking. I guess the way I see it now is that these are 64-bit pointers or addresses to other node objects of size, node size. So really, when we allocate memory for a node object, we're really just allocating memory for a pointer to a name, a pointer to another node object, and a pointer to a previous node object. All right, so now I think we can step back, making, again, sure everything is in order here. Can step back to the list object. I'm actually going to close out of node.h because I don't think I need it open anymore. And let's step back to get labels custom. Now that I have list objects defined, I can include the template for a list object and close out the files with those definitions. Okay, so now we've declared a path list or a names list. And actually we've declared a pointer to a path list or names list object. And this pointer is going to be the output of getPaths or getNames, which takes as input parameter the relative path to cocoa.names. Let's add now the declaration of getPaths inclusion guard. Opening it up here. The definition is, or the declaration is, getPaths takes in cocoa.names relative path and outputs a pointer to a list object containing all of the names for objects. And here we're going to need to include list. And now let's go ahead and create the definition. Just feeling things out for a sec. Okay. Again, we write out the function declaration or the function signature in this case. And include the list template. Okay. I don't think I want to test whether this method is working because, well, why not? So we're going to need to set return, let's say 0, so we don't get an error due to a method that should have an output not returning anything. And then let's include the declaration and here in getPaths include standard input output and say that we're using getPaths. Build error. GetLabels custom doesn't return, so let's return null pointer here too. And getPaths is working. Okay. I think I'm going to remove those and actually remove this just for a reminder that this hasn't been completed yet. And here we are in getPaths. So at least it's being called. Okay, so this method. So wherever there's the word path, you can substitute the word name. So we're getting names. Here's a declaration of a pointer to a string representing a name. We're opening cocoa.names for reading. We're making an empty list. And then we're getting each individual line from cocoa.names, setting the string or the pointer to a character array as the output of this getLineFromFile method, which stores strings in memory and returns their pointers. And we strip each string representing a name of any tab characters, for instance, and then insert that string into our linked list of names. We deallocate the file from memory and return our linked list of names of objects. So let's start working through this slowly. Declare a pointer to a name string, and let's create a file object representing cocoa.names that takes in the relative path to cocoa.names and a read option. And this is going to actually require the standard input-output library. And then here, let's declare our linked list of names. And declare a pointer to our linked list of names and set that pointer equal to the output of make list, which will make an empty linked list. Okay, so all of my, now all of my files are in order up here. We have to go down another level into make list. Let's do it. Here's make list. So in this method, we're allocating memory for a list object and returning storing the pointer to that memory in list object pointer to list object L, and then the size integer that is a property of the list object pointed to by L is set to 0, so 0 nodes in the linked list. And then the pointer to a node object within the linked list pointed to by L is the front node pointer is set to null pointer, and the back node pointer is set to null pointer, and then you return the pointer to the list object. Whew. I'm going to set up make list now. Declaration, first inclusion guard. And then we have no input arguments to make list, but we do output a pointer to a list object, so we need to include the list object template. I can close out this declaration file. And let's make the source file make list. Method signature, list template. Okay. So this would be easy, except we have to go yet another layer down into xmalloc, which is a custom memory allocation method which calls the malloc method from the malloc library. But let's start. So we're declaring a pointer to a list object. The pointer is called L. And this is equal to the pointer returned by xmalloc, interpreted as a pointer to a list object. So I'm going to pause here with finishing out make list, but let's check out xmalloc now. Okay, in this method, we're memory allocating a buffer of size t bytes. Just to confirm that, let's go to c++.com and look up malloc. Yeah, allocates a block of size bytes of memory, returning a pointer to the beginning of that block. By the way, this is where I find appropriate libraries to include for a lot of these methods like malloc. And it's also a great reference. So we're memory allocating a number of bytes, the number is size, and we're returning a pointer of unknown type to the beginning of that buffer. If the pointer is null pointer, i.e. malloc failed, then the program will end with a malloc error and an output message to console. Otherwise, we'll return the pointer to the allocated memory, which is then used to construct the linked list. So let's start by declaring xmalloc, inclusion guard, the output is a pointer of unknown type, the input is a size to allocate, and this is a method declaration, not a definition. We're done with the declaration. I'm going to copy this signature and let's create the method definition, xmalloc. Okay. Writing this out, we have the declaration of a pointer of unknown type, defining it as the output of method malloc from malloc.h, a system library, takes as input the size parameter. If malloc failed, then we throw a malloc error and stop the program. Otherwise, we return the pointer to the allocated memory. Let's go another step down into malloc error. I think this is as deep as we need to go right now. But here we output a message to console and then exit the program with an exit failure code. So for the malloc error method, we need a declaration. No inputs, no outputs. Here's the declaration. Close that out. Now let's go to the definition in a source file. The function signature, and we're printing out to the standard error stream that there was an xmalloc error and that we're possibly out of CPU RAM as a cause. For outputting to the standard error memory stream or the console, you need to include standard input output, and after the message is output to console, we exit the program with an exit failure code. And to use exit and exit failure, we need to include the standard library. That's it for malloc error, which is called if malloc or xmalloc, I guess, fails, or malloc fails. Malloc within xmalloc fails. There we go. Okay. This is as deep as we need to go right now, so I'm going to carefully back out. We can close malloc error. here we need to include it. I think we're good with xmalloc now, which will be used a lot in little YOLO version 4. So we can close out xmalloc. Okay, and now we can finish off making an empty linked list for names or for paths. Let's include xmalloc. So a reminder here, we called xmalloc to allocate a number of bytes required for defining a list object, and we return the pointer to that 0 initialized list object. And now we want to set the pointer properties of the list object all to null pointer to 0, and then return the pointer to the list object so that then we can fill the list object. So the integer size of the list object pointed to by L is 0 initialized as the 32-bit integer 0, and then we set the pointer front of the list object pointed to by L to null pointer, and we set the pointer back to a node of the list object pointed to by L also to null pointer, and then we return the pointer to this list object L. The pointer is called L. Okay. How these files get out of order up here, I don't know. But anyway, I think we're done with make list, so we can back out of that. Alright, so now we're back in the method getNames or getPaths. And the goal is to return a pointer to the linked list of all the names. We just created an empty linked list, and we're using the relative path to cocoa.names. So over here, the strategy is to look through the file object pointed to by the pointer called file to cocoa.names, to look through this file object and to return pointers to character arrays, or basically to look through the file and return strings. Set path to each string, each line, to clean up the string from each line, and then to insert the string representing a name into the linked list called lines. So let's take this section one step at a time. While the pointer to a character array representing a name and also representing a line in cocoa.names. It exists after we've searched for the next line in cocoa.names. Okay, so this while loop evaluates whether this pointer is non-null pointer-ish, whether it exists as a full string of itself. And so when getting a line from the file fails, i.e. we run out of lines, this while loop will terminate. This is both a definition or a redefinition and a Boolean expression at the same time. It's intricate. Now let's take a look at getting lines from files. So we're going down a few levels again. Over here in little YOLO version 4 for viewers, let's set up the declaration for fgetLine. Inclusion guard. And we write out our function declaration. So fgetLine takes the pointer to the file object representing cocoa.names and outputs a pointer to a character array representing the line or the name. And then to finish out this method declaration, we need to include standard input-output. Then let's write out our definition of fgetl. Outputting a pointer to a string requires the pointer to the file object. This is our definition. We're still relying on the standard input-output. Okay, so how does this method work? Well, we assume in a hard-coded fashion that all of the names are less than 512 characters. I think that's very reasonable. And then we define a pointer to a string that's just randomly allocated memory right now. And the bits are random. The allocation is done by this method, and the pointer to that allocated memory buffer is stored in pointer line. Then we attempt to change the bits in the memory pointed to by line by calling the standard method fgetl. We're trying to get the line from the file object. And if getting the line fails, we free the memory that we allocated for the hypothetical line, return failure for fgetLine, which then breaks that while loop that adds lines or names or paths to linked lists. If we got our line or our name from the file, we return the pointer to that line. Which then is stored here in the path or the name string is cleaned and then is inserted into the linked list of all of the names of objects. So let's start coding this method up. I'm just making sure all of my files are in order here. Okay. We're assuming all strings or all names are less than 512 characters. We're allocating memory for hypothetical names, and we might insert the actual stored names in this memory into our linked list eventually, but yeah, right now we're just allocating for a hypothetical name, which then we'll try to fill. And each of these names are given enough room each for 512 characters. Seems a little wasteful, but it's an easy method right now. And on modern computing systems, not a big deal. Okay, then we try to fill the memory pointed to by line. And this method is a member of the standard library, so you can look at it on c++.com. Do I even need that inclusion though? Oh, I need it for free, not for fgetl. Okay, sorry, it's fgetl is a member of the standard input-output library, I think, or maybe a member of one of the libraries that's included by standard input-output. Yeah, so we're trying to fill this memory with a name. If filling fails, then we don't need the memory anymore, so let's free or deallocate it and state that the filling failed. And for the deallocation, we need to include the standard library. If filling this memory with a name succeeds, i.e. it doesn't fail, then we return the pointer to the now filled memory. I'm going to back out of fgetl now. And include it here. So now we are in the process of getting each line from our file cocoa.names, and let's write out the functionality for cleaning each name. And that would be stripping the name of any tabbed characters, whitespace characters, new line characters, or return characters. So for this, we need to have our function declaration. Take a look at how the signature actually. So for cleaning, we take in a pointer to a string and work on that string by progressively, or I guess it would be in this direction for you, progressively moving good characters over toward the beginning of the string. And overwriting any characters that we don't want. And then at the end of our shifting process, we put the string termination character or the 8-bit message 0000000. Was that 8? Anyway. Yeah, so we're searching for the characters that we don't want in that. In case we find one, we shift all of the characters back. And then at the end, we put a new line character. So here's the method declaration. Going now to the definition. Source file. We're just modifying the character array that's pointed to by the input parameter s. Okay, so using the library string, let's find the length of the string and going here to c++.com, let's look up string length. The length of a C string is determined by the terminating null character, so /0 or the null character 000 is, anyway. A C string is as long as the number of characters between the beginning of the string and the terminating null character without including the terminating null character itself. So all of the good and bad characters other than the string termination character. And then we define a useful tool called offset and declare a character called C. That will also be a tool. So for each character between the first character in the string and inclusive and the string termination character exclusive, let's assign to character C the present character in the string. If this present character is the white space character, or the tab character, or the new line character, or the return character, increase this offset tool and don't add don't shift the present character backwards in the string if the shifting parameter offset is greater than 0. I guess you can shift by 0. So if the present character is a good character, shift by 0 or some present offset greater than 0, but shift each character unless it's a bad character, a character we don't want. If it's a character we don't want, then account for that it's a character we don't want, and then shift every subsequent character back 1 if we just found 1 bad character, or if we found 2, then we shift all of the subsequent characters back 2. And then after shifting all of our characters back, we put at the present location, more or less, or 1 after the last good character, the string termination character, which basically is what defines a string as being separate from subsequent memory. So that's the cleaning method. We can now back out of that. And we're still working with each individual name found from the file coco.names. We've cleaned it. Now let's insert the name that was found into our linked list of names. So we're inserting into the linked list pointed to by lines the name string pointed to by this pointer path. Here again we need declaration. Let's take a look at it. I think this file rearranging has to do with using this goto and how the subsequent files appear on the left. Okay. So, declaration for inserting names into lists. There's no return value because the linked list has already been zero initialized. We do take input parameters of the linked list that we're inserting into and a pointer to an object of unknown type that we're inserting into the list. This is our declaration. We need our inclusion guards first. And let's include list. And that takes care of all of the complaints. Now let's go to a definition of line. Did I say? Okay, this method is actually list insert. Here I said line insert, so I'm going to adjust that and make sure that this is list insert, which it is. Now go into the source file for list insert. We have our signature include the template for the list object. Okay, so how does inserting pointers to character arrays or strings work? How does inserting into a linked list pointed to by L work? So first, let's allocate memory for a node object and store the pointer to the first byte in that allocated memory in a pointer called new node. So we're basically creating a node object in which to store our string, and which will have memory. We'll kind of know what the next node is in the linked list. So really the linked list object only has information on its own size and what the front node is and what the back node is. The nodes in between have the information on what the next node in the list is. So the list object template size is pretty small, but the linked list can be as large as your RAM, basically. Okay, so we've created a node for our string and for information about other strings. So we're setting the pointer to a character array of the node object pointed to by new node equal to the string that was passed in, that we're inserting into the linked list. And this new node is the last node in the linked list. So if you imagine a linked list starting here on the left, and let's say it has 1, 2, 3 nodes with strings already, then we're inserting a new node at the back here, and the next node after this new node that we're inserting doesn't exist, and so the pointer to a future node of this new node right now is null pointer. So writing that in code here, the pointer next of the node object pointed to by new node is null pointer. Okay, if the pointer back to a node object of the linked list pointed to by L does not exist, so if the linked list has no back node, thus the linked list is empty, we want to set the present new node as the first node, or the front node over here on the left in the linked list, and say that the present node, the new node that we're inserting, doesn't have any previous nodes because it's the first node. And thus we insert, or we set the previous pointer of the node object pointed to by new node as null pointer, writing all of that in code. If the back node does not exist, set the front node of the linked list equal to the new node, and say that the new node has no previous nodes. If there are some nodes in the linked list, whatever the present last node in the linked list is, so over here, it has a next pointer equal to null pointer right now, but we're inserting the new node, so we need to set this rear node's next pointer equal to the address of new node which we're inserting. And then we also want to say that the new node that we're inserting has an address to a previous node in the linked list of the present last node in the linked list. Okay, so if there are nodes existing in the linked list, then set the pointer back, or set the pointer next of the node object pointed to by back of the list object pointed to by L as pointer to node object new node. And then the node object pointed to by new node has a previous address to a previous node object of the address of the node pointed to by back. And then we change the back property, I guess, of the linked list pointed to by L to the address of, or the address of the node object pointed to by new node. And let's also change the size property of the linked list. We're incrementing it. So we've allocated memory for a node object that contains 3 pointers: a pointer to a string that we're inserting into a linked list, and a pointer to a next node, and a pointer to a previous node. We've also updated some properties of the linked list itself. So we've inserted a string into a node, we've inserted a node into a linked list, we've updated the linked list. I'm going to back up one from this list insert method. Change this from line insert to list insert. And now I will include it. Okay, so now we're back here in the method getPaths, which inserts names from coco.names into a linked list pointed to by lines. We've basically created the linked list and filled it. Now we're ready to free the memory associated with file coco.names and return the pointer to a linked list containing all of the names. So let's free the memory associated with coco.names and return the pointer to the linked list of all the names. Now we can back out of get paths. Here we include it now that it's done. Okay, so now we have a linked list of names of objects that were drawn from the file coco.names. We're now ready to take the names out of the linked list and put them in an array of strings. So let's first declare our array of strings. And let's define our array of strings as the pointer to an array of pointers to character arrays, which is the output of the method link of list to array, which takes a path list or a names list and converts it into an array of strings. How does list to array work? Going down again. We declare this method. This is a declaration. Now we need our definition. Here we have a zero initialization, so an allocation and a zero initialization of a character array, or actually a zero initialization of a buffer for a number of pointers equal to the number of names of objects. And for each object, for each name in the linked list, we're iterating through the nodes corresponding to each name and changing the 0 initialized memory we're changing the null pointer corresponding to each node or each name to the pointer to the character array representing the name, or the pointer to the string name. Okay, I'm just going to play here and change this C to an M and temporarily include xmalloc and xcalloc and xmalloc have two different argument configurations. So instead I'm going to rewrite the xcalloc call to an xmalloc call. So this is the number of pointers to names, and this is the number of bytes per pointer. I'll comment the calloc out and the calloc out. Basically, I'm trying to eliminate the 0 initialization. I'm okay with just random bits because all of those bit values will change in this statement. Everything's still working. So it's just, the program's a minutely bit faster now. I'll stop. Okay, so let's write this out. We're declaring a pointer to an array of pointers to name strings and allocating memory for that pointer to an array of pointers of name strings. Then count is basically the index of the present name in the linked list of names and also the present name in this array of names that we're creating. But we're using count as and incrementing count manually because to iterate through linked lists it's best to use a while loop as seen. So we're initializing count to 0 and then let's declare a pointer to a node object n and set this pointer equal to the address of the first node in the linked list of names. While this pointer is not null pointer, so while, and right now, because there are names in this list, n is not null pointer. When n is adjusted to be the next node after the back node in the linked list, then n will become null pointer and this while loop will break. But while this node exists, basically, we set the present pointer in the array of pointers to names as the string property of the present node in the linked list of names. And then we increment count. I'm just going to make this, I think, a minutely bit more readable and change this to the count element of the array of names, and then I'm going to increment count separately. Let's see if that works. Yeah, I think that's more readable. And I hear that having plus plus count is faster than count plus plus. Then, after we've assigned the count element of the array of names equal to the string in our present node in the linked list, we set the pointer to the present, the pointer to a node in the linked list as the present node's next node address. And then we've iterated through the entire linked list, adding the name strings to the array, and now we can return the array. Closing out of list to array. Let's include the template for list to array. Now that all of our names are in an array instead of a linked list, let's free the list of names. This is a custom method, so let's check it out. function declaration requires the list template. Then we make our function definition. Nope. Include the template of a list object. Okay. And how does free list work? Well, first we have to free each node from memory. And then we free the memory associated with the linked list. This is a standard method. This is a custom method. So let's go to the custom method. First, I'm going to write out the call. We're passing the address of the first node in the linked list. Declaration. Definition of free node. Okay, so free node. While the first node exists, define next as the next node after the first node. Free the present node, and then change the present node to the next node. While n is the second node, find the third node, free the second node, set the pointer to the second node equal to the pointer to the third node, etc. And then while the last node exists, look for the next node. It will now be null pointer. Free the present last node and set the pointer to the present node as null pointer, or and then while null pointer is false. And so we've deallocated the memory associated with each node. Writing that out. For free, we need to include the standard library. We're done with free nodes, so we can back out of that. And then I can include it. And now that we've freed all the memory associated with the nodes, we can free the memory associated with the linked list itself. Notice we're not freeing the memory associated with the strings. That's obvious. And I need to include standard library here. We're done with freeing list. And then I can include free list. And finally, we've now read names of objects into a linked list. We've converted the linked list into an array. We're now freeing the linked list, and then we can now return a pointer to pointers to strings, or a pointer to an array of names. That takes care of getLabels custom. We can close that out. Now we're back to test detector and how this is acquiring the names that will then be placed above the bounding boxes that you see in a lot of tutorials of YOLO version 4. I've taken the time to put together a testing of getLabels custom, so let's take a look at that. It's simple. So for name size doesn't exist anymore. How do we want to do with this? Well, I'm gonna cheat, I think, and just see if I, without an access error, look for the first 100 names. Let's try that. And I've included single quotes around each name just to make sure that each name is clean of white space characters. And this is for testing names, include the standard input-output library. Let's see what happens with this. Didn't like it, but this seems like a can't get not an issue with this for loop. So let's do a little debugging here. Looking at the project properties, we have cocoa.names there regarding little YOLO version 4 for viewers here. Well, we don't have a data folder, so let's work on that. Looking here at the little YOLO version 4, we have a data folder, and then this is our names file here. So let's, here in Yes, this is the write and root folder. So we need a data folder, and then let's copy over cocoa.names here. Closing those out for a little bit. Let's give this a shot. Well, there was definitely an exception, and this is an access violation because we're trying to read characters from out of allocated memory. But here we see all of our names anyway. So I think it's working. I could have included a new line character, but it really doesn't matter. Going back to our little YOLO version 4 for viewers, loading it up. The last three are toothbrush, hairdryer, and teddy bear. Toothbrush, hairdryer, and teddy bear, with their white space characters removed. That makes sense. I think we're good. Thanks for watching.